Is it all? Is it separate? Get these pictures figured out.
I made some progress on it.
That's all. That's what it looked like. You would make nice impression.
And I didn't get a chance to think about it yesterday because I was grading tests all day.
That's fine. You go on Monday.
Mhm.
What day is it? You're the boss.
Well, that's what I'm going to check.
It's seven.
Is this how this works?
Yeah, because last time it was 16. Okay, well, maybe we should start.
This is it.
So I finished last time by defining a membrane system for a trivial disk tangle, is that right? Okay, and then your exercise was to come up with equivalent definitions for a disk tangle to be trivial. So let's see what you guys came up with. So we'll start with a C-disk tangle, and what we want to do is characterize triviality in some number of ways. So the first we have is trivial. And I guess the definition of trivial meant that the disks could be isotope relative to their boundary to lie in the boundary of Z. So what's another condition for a disk tangle that is trivial?
Sorry, the definition was isotope to the boundary.
It has a method system.
Yeah, exactly. So a membrane system for a disk tangle is an embedded collection of three walls, half of whose boundary is on the disk tangle and the other half of whose boundary is on these shadow disks. And that's just the trace of this isotope. Okay. How did I define disk tangle? Did I? So in my notes I have it that there's the disks can be isotoped and have no saddles. I don't think I said that. Okay. After isotope is all boundary, age restricted to D can be has no saddles. Okay, so just to recall, H from Z to I guess maybe negative infinity to 0 is a height function, radial Morse function, because Z remember is a copy of it. You don't like Z?
No, it's a ball radius 0 is centered minus infinity.
Yeah. Oh, did I do it backwards?
No, I don't know.
No, that's right.
Fine, that's what you mean, right? 0 is
Yeah.
fine, right?
Yeah, exactly. All radius 0. Okay. There's a fourth condition. Did anyone come up with any other characterization of this? Okay. So the fourth condition is that ZD is, I guess, diffeomorphic rel boundary to a trivial tangle cross I for some trivial C tangle. So I think this is kind of an interesting characterization. If you start with some trivial tangle, let's no, this. Maybe I'll draw it kind of like this. Oh, I know how I want to do it. Okay, so this is meant to be B, this is meant to be B bar, and this whole thing is meant to be C. So we start with some, maybe I'll even add some crossings just to make it interesting. We start with some trivial tangle there, that's T. And then we cross with I. And then so when we cross with I down here, we're going to get some tangle. Well, we're going to get T bar. And then what we see in between is a little bit difficult to draw there around the twist regions. But what we see in between is a collection of properly embedded disks in this 4-ball. So here, instead of crossing honestly with I, I've sort of pivoted. Maybe I'll fix it a little bit like this for Dave's sake. Something like this. Take a little disk there. Bigger disk out here. Okay, so hopefully that's becoming something of a clear picture. So these are the same picture where here I've compressed the vertical boundary part and thought of it as sort of swinging instead of crossing. So this should give you an idea of why if we take a trivial tangle and cross it with I, we get a trivial disk tangle. But of course, how would you actually prove that that's what you're getting? What would you use to argue that this thing is a trivial disk tangle?
Which one? That the one on the right?
Well, I guess either one. Yeah, maybe this one. I mean, I guess you can use almost any characterization of trivial tangle. So since this is boundary parallel, you can use the boundary parallelism cross I and just push this whole thing. Or you can take a membrane system and cross that membrane system with I and get a bunch of balls. Give you a membrane system for the disk. Okay. Cool. So far, disk tangles seem a lot like regular tangles, almost redundantly so, right? But I think, Thomas, last time you said something about doing these jumps and slides and stuff. Okay. So things get a little bit different here. So the proposition is, suppose that D1 and D2 inside Z are trivial C disk tangles with boundary of the first one equal to boundary of the second one. Okay. Then D1 and D2 are ambient isotopic rel boundary, rel their common boundary. Okay, so this is a major departure from tangles, because when we were thinking about tangles, you know, we have our favorite tangle, and then we have some other tangle with the exact same boundary. And these tangles are definitely not isotopic row boundary, because we can glue any two of these tangles with the same boundary together to get any knot or link. Okay, so these are not isotopic row boundary. On the other hand, any two C-disk tangles with the same boundary are ambient isotopic row boundary. Okay, so let's look at the proof of this. I debated how much to talk about this, but well, let's do it. It might seem quite familiar. All right. So we're going to try to do this three-dimensionally to the extent that we can. So the first thing we're going to do is we're going to isotope, so ambient isotope row boundary, the DI to lie in boundary Z, such that D1 intersect the interior of D2, maybe the cardinality of this is minimal. And then minimal is, you know, over ambient isotopic gases. Or something. That's right. Just minimal. We know what minimal is. Okay, so and let's get a picture of this. So we know what the boundary of a trivial disk system is, right? It's just an unlink of some number of components. And so, sort of without loss of generality, we can assume that one of our disk systems sort of looks as nice as we want. So let's suppose that yellow is our disk system D1. And then what does blue look like? Well, there's sort of a couple of cases. I need to have a disk that emanates from each of these curves, but it could sort of intersect the yellow guy in complicated ways. Okay, so maybe it does something like this. Okay. And then, guess what does this one then have to do? I get myself into trouble here if I'm not careful. Okay, so that one kind of goes around there. Also, I'm going to make the picture look not so good. And then this one, maybe I'll redraw this one up here so that it doesn't get quite as complicated. This one, I kind of want to do this. See if I can draw it. Just as an example. Maybe that's what's going on inside that. Okay, so we've got these two disk systems for these two disk systems in this three-sphere boundary for the same unlink. And what we want to do is we want to prove that they are isotopic to each other. So the first thing you might try to do is just isotope them to each other inside the three-sphere. But this is definitely not going to be possible because we want to do it relative to the boundary of the disks. So for example, we can't move this white circle. So you can just sort of imagine there's not going to be any way to get rid of this intersection without moving this. I mean, so let's make that a little bit more precise, right? normally the way we would remove this intersection would be to find the three ball that is sort of co-bounded by this innermost disk and this disk, and do an isotopy across that three ball. But that three ball is going to intersect these white curves. So can anyone guess what we'll do?
I don't understand this.
This picture?
Yeah.
Well,
What's the blue disk?
it's a disk. Imagine I started with the yellow one and I sort of just pushed it down along the interior of this semi-disk and I pushed it up along the interior of the semi-disk.
Blue goes
It's like this picture.
and down.
I can see the down part. Oh,
Because
it
it's
actually
blue.
crashes through the other.
It crashes through,
The
yeah.
intersection with the yellow part is a line.
Oh, that's the picture.
Yeah, there's an arc of intersection. So here we have an arc of intersection between disks. Here we have a curve of intersection between disks. So, and that we want to clean those up. Any guesses before we actually do it?
Which we got the more from use, like, if we like put some other system and we have like surfaces, then we might be able to use a spore in order to solve that actually good idea is unknown in the spore.
Yeah, I think that's the right idea. So like if we were trying to do this three-dimensionally, we would want to take the union of this disk and this disk. They bound a three ball at S3. We want to push this disk across that three ball, but we can't because this is in the way. But what we can do is push that three ball into the four ball and push the disk across the three ball, sort of below the surface, and then back out so that it comes up. So it's basically the idea. So this is so let's just write it out now that we've come this far. So the first claim is that D1 intersect the interior of D2 contains no closed components. Okay, like that red curve over there. So if so, choose an innermost curve C inside this intersection. I wrote innermost, but where is it? Innermost. Innermost, choose a curve such that C is innermost in D2.
I'm a little confused because the interiors of the discs are supposed to be in the interior of the four ball anyway.
Yes.
Generically, they're going to intersect in points, right? Not curves.
The isotope everything into the boundary,
The first step was to isotope everything in the boundary.
and there they intersect.
Oh, why did we do that?
Well.
Okay, so that you can make a three-dimensional argument.
Yeah.
Okay.
So we can make a modified three-dimensional. Yeah, it's nuts. Yeah, it's a little less clear how you would do it if you had these disks, intersecting points.
You need to use the fact that they're trivial,
Uh-huh.
which means you need to somehow use the fact that when you push it into the boundary, they're actually embedded disks.
Right. Although you could probably use one of the other definitions of trivial, like maybe. I thought about this a little bit. Maybe use the fact that each one can be isotoped to have only one minimum, and then you use just that fact to remove any points of intersection. That would be a different proof.
Okay.
Okay. So we're going to let EI be disks in these disk systems. Be disks so that the boundary of EI is C. And we're going to let Q be the union of these E's. Okay. And we're going to let B be a three ball in S3 with boundary Q. Boundary and B equal Q. And then we are going to assume we're going to push the interior of B into B. So B will be properly embedded. Okay, so for example, in this picture, we would have maybe this red innermost curve in D1. No, innermost in D2. I guess it's innermost in both of them. And then the ball we would use would be this guy in here, which we then push into the 4 ball. And then the last step is to push E2 across B to coincide with E1 and then push it off. So we're doing this push, except it's happening just below the surface, so that push doesn't cause this disc to intersect the knot, and it pops out right here, this thing. And then we've removed an intersection, and so that's a contradiction that we actually had minimized this intersections to begin with, and in this way we can get rid of all closed components. Okay, and then claim 2 is that D1 intersecting the interior of D2 contains no arcs. Well, I guess it's empty. Okay. Now that we've ruled out closed curves, all that we could have would be things like this, and arcs. Although to make this picture a little bit more realistic, we should remember that inside here, we can sort of have these kind of like guys hanging out inside here, right? That might be making it hard to fix these discs. Okay. But I'm not going to spell out the details here because it's really just the same argument with a slightly different choice of cue. Okay, so now after these two claims, we have that D1 intersects the interior of D2 is empty, but we could still have things like this picture. So maybe we've got some things like this. Okay. This is a possibility for what D1 and D2 look like. It's not automatic that they're isotopic in S3 at this point. And so, well, we repeat the process to make D1 equal D2. Okay. So in particular, you would do something like choose this disk to be E2, choose this disk to be E1, and over here, what did we do? We pushed it across the ball until it coincided, and then we pushed it off. Well, here we just pushed it across the ball until it coincides, and then we're super happy. Okay, so and I should say this is a pretty old proposition. It's not actually clear who it should be credited to. There's a paper of Chuck Livingston where he proves that any two Seifert surfaces for an unlinked with the same Euler characteristic and the same boundary are isotopic in the 4 ball. So this would be a corollary of that. But there's this earlier work on sort of these this normal form like this Kawuchi, Shibuya, Suzuki. I think they cite even some work before that where this is proved. It also appears in like Kamada's textbook on braided surfaces, but that's like much later, but some people still cite that as the source. Anyway, this proof that I gave is basically the way Alex and I thought about it when we were trying to prove it in a more general setting where Z is a 4-dimensional one-handle body instead of just a 4 ball. Any questions? So trivial disks with the trivial disk tangles with the same boundary are going to be this topic. Okay. All right, so let's see if we can tie this back into what we were talking about. Remember, we were talking about normal, putting surfaces in normal form. And when you do that, what you're interested in is you're interested in this coordinate of saddles between unlinks. And so at some point, what we'll want to do is we'll want to say, oh, if we get this unlink at the bottom, there's going to be a unique way to close it off with caps. That's where this proposition will come in. Okay. So a banded link LB is an unlink L a pair LB such that L is an unlink, B is a collection of bands for L, and the third hypothesis is that when we resolve L along the bands, we get another unlink. So this is a little funny to be defining this at this point because we've basically been talking about these objects for the last couple of days, and I've drawn pictures and stuff. So as an example, all of the things that I talked about this week, if S in S4 is in normal form, then the intersection of S with the equator is a banded link. Remember, in normal form, we pushed all the bands into the equator, so we precisely see L being the minima, the boundary of the minima, the bands being all the saddles, we have a banded link, and then we resolve and we get the unlink corresponding to the maximum.
So that's only with half the bands though?
All the bands are in the equator for normal form.
Okay.
What do you mean by half? Are you thinking half come before the equator and half after?
Yeah.
See, that's where you know, that normal form means we put all the bands in the same level. So below that, you basically have the boundary of the minima. All the bands appear, you resolve them, you have the boundary of the maximum.
So I'm
Self-indexing.
thinking from the middle, you can resolve along half the bands to get unlinks.
That's true.
Or resolve the other half to get an unlink down here. But you're saying resolve along all the
That's
bands.
true, but so okay, let's drive this point home because I think it's
He
important.
doesn't want to have that middle level, he just wants to push all there. So it's unlink, bands, unlink. And you just didn't, you were
But that's
you were
unclear
sleeping
to me
with it
that-
when the knot was visible.
That's unclear to me that was
Okay.
getting unlink. Like you've got an unlink up that way and an unlink down that way.
Let's be very careful about this. So all right, so one way to think about, here's a knotted surface. We could think of this knot K as sitting inside the equator of S4, and we could attach the blue band going down. So let's draw a schematic here. So in this schematic, our central cross section is K, and then some point higher up, we see. Oh, sorry, I decided that one's going to be down. Go away some others. So maybe this is K. This is K higher, and this is K lower. Just see if we can be really careful here. And we have this band B1 down there at height -1. But then we also want this band. B2, and this one we think of as going up. Okay, B2. And it's easy to check that each of these give unlinks. And so we have a surface. Now, by definition, this surface is not in normal. Because when a surface is in normal form, all the bands are contained in the central cross section. So it's just a particular thing you ask for. So the way we can think about this as being in normal form is we need to, instead of living in this S3 cross section, we need to sort of go down below both of the bands, and we need to push them into the same level. So the banded link for this surface is this guy. Now we resolve this. And we look at the dual band of beta 1 dual. And we still have beta, we still have B2 here. But this now is an unlink. So L is the link of two components, and L resolved along beta 1 union beta, or band 1 union band 2 is also an unlink of two components. So that's where band link is. And this is rather important, this sort of distinction between these two components. It's a constant struggle. So yeah, and actually maybe the way I approach this lends a little bit of confusion, because after I sort of introduced normal form, then we went on this detour towards thinking about knots and ribbon surfaces and slice disks, and so we immediately adopted sort of the non-normal form perspective. Okay. So we've already seen that if a surface is in normal form, then the equator is a banded link, so there's a converse to this. LB, be a banded link. Comma. And let S and S4 be the following surface, and it will in fact be in normal form. Or maybe I'll write that as a conclusion. The following surface. Okay, so I'm going to describe this surface in pieces. So the restriction of S at height 2 is going to be D plus. So this is going to be trivial disks in this cross section. So just an unlink with a collection of spanning disks. Going down between 0 and 2, we will just see the resolution of L. Oh, yes, I should say. Resolution of L. Oh, yes, I should say. Trivial disks in S42 spanning the link L beta. And so going down, what we see is just L beta. This is my notation for pushing L beta straight down. And then in the center, we see L together with beta. We see this 2 complex, which is the banded link. Going down further, we have L flown through in 2-time interval. And then at the bottom, we see another trivial disk, D minus, which is trivial disks spanning L. So now that I've written all this, it's actually easier to think about it going straight up. You start with the unlink L, you vertically go up, you band to this flat level, and then you vertically go up by the resolution. And then this gives you an unlink up top and an unlink up bottom. And then you want to choose a set of spanning disks for that. This S is called the realizing surface for the banded link. Okay, and then the proposition is that every surface link is isotopic to the realizing surface for some banded link. And conversely, I think I wrote it somewhere. Every banded link encodes a well-defined, this is added to that line, well-defined surface link in normal form, I guess, via the realizing surface. Okay, so I think we've essentially already proved everything in this proposition. We've already seen that we can put a surface link in normal form, and we've seen that once a surface link is in normal form, we can then associate the equator cross-section to get a banded link. And maybe the only non-trivial thing here is that if a surface link is in normal form and you take the equator level and you take the realizing surface for that, so if S is in normal form and LB is the equator, then the realizing surface for LB is S. Okay. And I guess when you do this, one thing you need to know is that the choice of trivial spanning disks here doesn't matter. And the reason it doesn't matter is because suppose I chose the wrong choice here, well, I can perturb them farther down below the -2 level and then back up to realize the proper one, since any two trivial disk systems are anti-isotopic robot. And then what about for the other direction? Every banded link encodes a so well-defined is what I just said, that there's a well-defined way of capping off the top. Any questions? Okay, so we're closing in quickly on bridge trisections. Okay, there are things called banded link moves. Okay, so we have this sort of diagrammatic representation of a banded link, and so there should be some moves that we can do to the banded link that present. And so we've already seen some of these things. How do I want to present this? So the first one And these are all local moves. So this move is supported in a 3-ball neighborhood of a band, B1. And what we see in that 3-ball neighborhood is the foot of another band, B2. And what we're allowed to do is move the foot of this band over B1 to the other side of the B1 bridge. Okay, so this is called a band slide of B1 or B2 over B1. And if you want to think about why this works the way it does, you can think about B1 occurring slightly lower than B2. Okay, so coming up to B1, we sort of have this picture. Or this picture, our surface is coming up, and then we see B1. And then after B1, we have this picture. Oh, it's sloppy there. But you see that the boundary of the new picture is of a different form. So it's L resolved along B1. And this is where B2 lives. I drew this as small as possible for some reason. But B2 lives here. And when we consider a band for a link, we are allowed to move the endpoints of that band along that band. Okay? And now the link that B2 is belonging to is just, it has a piece of its link running along the edge of B1. So we can just move it over to here. That's just an isotopy of the band, which it fixes this link setwise and accomplishes this slide. And then we push it back down into the same level. And similarly, we could also slide B1 over B2 if we sort of isolate a ball neighborhood of B2 and do the exact same thing. So we're able to slide a band over another band. And it's because it's this picture which tells you, well, why don't the endpoints of B2 just move past the endpoints of B1? And this is why. Okay, so that's a band slide. And we saw this already when we were trying to arrange that the bands were in the same level, because it could be that the endpoints of the band ended up on here. And so we had a choice of which way to move them off to get our sort of banded link, our normal one. But so that should have been a little bit of an alarm in that, well, what if I choose a different way to resolve this problem? Well, fortunately, they're related by a nice move. Okay, so let's do the swim. We'll stick with our neighborhood of B1. This time, B2 is going to do this. And the result of the swim is going to be that B2 appears magically on the other side. So this is called a band swim. Of B2 over B1. And so what's going on here? Well, what you should think about is B1 has this core here, and we're just passing B2 through B1 along this core. If you had a picture where B1 is twisted, this gets a little scary. But this picture, once again, tells us exactly why this should happen. Let's see if I can just recreate it real quick. Make it a little bit bigger.
Yeah, draw V1 as blue this time.
Drop B1 as blue?
Yeah.
Why?
It's gonna be swimming through.
Oh. Bill. Don't tempt me. Okay, so so now we're up in this level, and what is B2 looking like? Well, this is actually a little funny to draw. It's sort of living up here, and it sort of goes under there. And you just have to remember that we have a three-dimensional cross-section here, so there's no real problems. But in this cross-section, there's nothing there. And so it just comes over. So it swings through the empty space. Okay, two more moves. These ones are a little bit simpler and a little bit more novel at the same time. So here we just take maybe I'll draw the neighborhood. Confused by this yesterday. In this local neighborhood, what we do is we just take that piece of strand and we add on a band with a little cut. Well, I spoiled it, but what does this correspond to doing in the Morse 2 function? In the normal form. Well, it looks like this. It's adding a little minima, a cut, and it's canceling it. So this is called a cut. And then lastly, as you can imagine, there is a cap. This kind of highlights sort of the asymmetric difference between cups and caps in a banded link, because then what do we see? How do I draw this? We have this sort of flattened boundary. Something like that. All right, so what we've done is we've introduced a canceling maxima. This is called a cap. Okay, so these are the banded link moves. And the theorem, which was sort of first addressed by Swenton in 2001, and then in a little bit more detail by Kierton and Curlin in 2008, who gave a little bit more of a rigorous sort of singularity theoretic proof of how you can mess around with these relative Morse functions and find paths connecting them. And what happens when you pass these, what are the codimension one things called that block you? Walls. Something else? Strata. Walls. Okay. Anyway, the realizing surfaces of two banded links are isotopic if and only if the banded links become isotopic after sequence of banded link moves. Okay, so this is great. I mean, we have a diagrammatic way of understanding knotted surface three-dimensionally, and we have a calculus of moves that allow us to go between them. So what we'll do in the next couple lectures is transform this perspective into the bridge trisection perspective. All right, have a good weekend.
You too.
Any questions?
Yes. I don't really get the swim picture.
Because it seems like this is like intersecting, or?
Yeah.
Well, that's the fault of the picture. Because this bit where it intersects, that is lying at a lower time than the band. The band is lying at the time that corresponds to the top of the wide structure. The fact that the band goes below this piece of the link is different. That's a different below. That's a below in S3. And that down there is a below in the time. Yeah, so it's a bad picture in that sense.
Interesting.
But so, and if you want to drive this point home, I would encourage you to draw these pictures with time slices. And then you'll just see.
Just go down until the band's not here and move it across.
Yeah, exactly. After you move past this band, it's just gone. There's nothing there. And so you just move right through.
The red band is at one time, and at the same time as the top.
Exactly.
All
Band is
these
at one time.
Different things are different times.
That's right. Yeah, that's exactly right.
The end time goes